Oh, there's a different E at electron and proton.
It's the same charge.
I mean the E.
Which?
The electric field strength.
Oh no, it's the same formula for both.
But AE. I mean, we have electric field strength.
Yeah, I think the answer's going to be the same. Is that what you're asking?
Yeah.
Yeah. Do you mind giving Jerry a gentle nudge? Sleepy time over now. Back to class. Okay, alright. Take a second to wake up. You fell asleep quickly. Very asleep. Deep sleep. Good sleep. Dad even. I'm jealous.
Me too.
I wish I could fall asleep that quickly and that deeply. Jerry, do you need to go get some food? Or will you be okay?
Oh.
Yeah, there's just half a sandwich there. Wait, what if...
Pancake.
That's fine. Everybody is doing question 1 now, okay?
Yeah.
You're on 2? Good for you. Trying to do that discreetly.
Teacher.
Yes.
For question 1, if you use the formula E equals to 1 over 4
Yeah.
and the Q, we use the electron on the proton.
For which part now?
A.
Electric field caused at the electron's location, caused by the proton. So because it's caused by the proton, it's the proton's Q you use.
Even the question asks E at the electron.
Yeah, because my question is how strong is the field where the electron is, and the field is being caused and is coming from the proton.
Okay.
If it was from electron, 2 pieces there, it would be minus one.
No,
Yeah, I don't really care about the minus because that's just for direction. So once you draw it, it's fine. The mass is definitely important. Yeah.
In this case, it's okay. What's the weight of the electron?
It's on your calculator. It's one of the. Oh, sorry. I take that back.
Yeah.
For which one? definitely.
You're fast.
Maybe you're slow.
That's a speed. And then, I think she...
Got an answer finished, Bruce? Sean? Good, okay, C, okay. Are you finished too, Monica? Yeah. Do you understand what I'm asking, in truth? Essentially, you will need to consider the smoke moves the full 30 in the worst case. Which part are you on, Chrissy? Which part are you on? Are you finished number 1? Good job. Who else has finished number 1 now? Monica's finished. Are you finished number 1?
Yeah.
Okay, so will we look at the answer for number 1 now? I think we will. Okay. 1 electron, 1 proton. Proton, electron, and the proton makes a field. And my question is here, what is the field strength? So the formula is 1 over 4 pi epsilon 0, what's the distance? 10 to the minus 10 squared. And is it the proton or the electron on the top?
Yeah, the proton.
Proton, although not that it matters for the number value. Well, I don't need to type that in because I'm sure you typed that in correctly. So what did you get in here?
1.44.
Yeah.
10 to the power 11.
Newtons per coulomb. Okay, B. What is the force experienced by the electron from the proton's field? Well, that's just F equals QE. We know the E, and what Q am I using? The proton or the electron? Electron. So E times 1.44 times 10 to the 11. And what did you get for that?
2.307.
Yeah.
Times 10 to the power
Negative
8.
8 newtons. Okay, C. The acceleration. Well, that's just A equals F over m. And we should divide by which mass? The electron or the protons? Electrons. Acceleration experienced by the electron from the proton, yeah? So, electron, yeah. So what's the answer? Oh yeah, it's on. I gave it to you. Yeah. Did you have it in your notes, the mass? D. Huh? Acceleration.
Yeah.
Meters per second squared, isn't it? Yeah. D. Now, did anybody get the periodic time? No. Okay, well, let's have a look at how to get that, okay? So you have T equals 2 pi over omega. Okay? Do we know the omega? No, we don't. But we can use the formula 2 pi over omega is V over R. Okay? But the problem is, do we know the V? No. Well, at least we know the R. Huh?
Omega.
Oh yeah, I have to use that now. So we have the other formula. Oh, I suppose I actually don't need to do it this way because we have the formula F equals m omega squared R. Yeah. Oh yeah, which is equal to ma.
A equals to
Yeah, there's multiple ways of doing it. So you could say A, which we know, equals omega squared R. So the A over R with the root is the omega. So this is 2 pi root R over A, which we both know. So let me just double check that one. 2 pi root, well actually it doesn't matter because it'll be the same thing. What was the A? 2.53. Tiny. 3.95 times 10 to the minus 16.
Teacher.
Yeah.
So A equals to omega squared R.
Yeah.
Okay.
Alright, continuing. The electric field at the proton's location caused by the electron. So if we go back up here, you might say, well hang on, the electron has a field too, doesn't it? So you might say, well how strong is the field here? What does the... And in fact, it's the same, because it's the same numbers. So it's the same as A. And the reason it's the same is because the charge for an electron equals the charge for the proton. Yeah, well, as I said, KJ, the minus is only indicate the direction if the field is going out or in, and strength doesn't need the sign. It's a strength, it's a number. F. Yeah. The force experienced by the proton, the same as B. And the reason for that was because the F equals QE, and we just said that this is the same, and we just said this is the same. So actually, if we calculate it, we get the same answer. But the last part now is interesting, is the acceleration. The acceleration experienced by the proton, and this is different. A equals the F, which is the same, but now the mass is different. This is for the proton. So what did you get here, Monica? To the minus or plus? Which one am I doing? I was expecting this to be small though. Is it, what was the acceleration you got for the electron? Oh, 22. Oh, okay, so it is smaller, yeah. 10 to the 19 meters per second squared. So what? Well, that's important. It means that the acceleration for the electron is about 1,000 times bigger than the acceleration for the proton. So both of them are actually accelerating. Here's the electron and here's the proton. It's quite clear that the electron is accelerating because it's moving in a circle. So there's definitely an acceleration here. But what's the proton doing? The proton has an acceleration. Now it's 1,000 times smaller, so you can't really see it, but it is accelerating. But how? Any ideas?
Speed.
Good, but not this. Yeah, what is it? Yeah, it's actually oscillating, vibrating. But it's not really important or noticeable because it's 1,000 times smaller than the electrons. You know, so if your calculations are 3SF, then you don't really care so much that the proton is accelerating. So in fact, you can imagine that the proton is not moving, it's fixed. But in real life, it's actually vibrating. Yeah? Okay. Let's see now number 2. Number 2.
In order to not accelerate.
Yeah. So you're trying to find the...
F equals 0.
Basically. Or the force of gravity is cancelled by the field pulling it back up. One sec. Yeah? Yeah, what were you saying? Oh, it just means here's the positive plate and here's the negative plate. Firstly, would the charge need to be positive or negative? And remember, the positive's on the top and the negative's on the bottom. So what would the charge need to be on the 1 gram? Positive or negative? Negative, because it needs to be pulled up to the positive plate. Oh, because I want no acceleration, so I want all the forces to balance. It was being... Yeah, well, no, just because it's not accelerating doesn't mean it's not moving. True. Still move up at a constant speed. You don't need to consider it because I've given you the speed of the smoke, and the smoke we don't really imagine gravity acting on the smoke because the smoke is hot. It'll be rising at a constant speed. The sort of buoyancy cancels out the gravity it experiences. So it's as if it moves through space weightless. No, there definitely is an answer for 3. Yes. Yeah, horizontal force. No, mg should equal QE.
Yeah. So the charge is on the object, not
The 1 gram, yeah. Oh, well, the plates are charged, but it's the charge on the 1 gram I want you to find.
Okay.
Yes. So mg equals QE. Oh, sorry. There is a force horizontally. Because there is a field between the plates. It's a Stephen classic. Yeah, but you know I love these questions where it looks like you don't know enough. What you do? It's a Stephen super classic. I'm going to do it, and you're going to be like, oh, of course.
What is the dot?
The what?
Oh, the dot. Okay.
Were you reading perdust as one word? What's a perdust particle? Alright, let's have a look at number 2. Number 2 should not take as long as number 1 to do. Yes, okay. Are you being dirty? Okay. Now, we have...
What?
I said number 2 shouldn't take as long as number 1 to do, and then he laughed, realizing that it's usually the other way around. Play it cool. What? Okay, so here there's 2 forces acting on this particle. This is just the gravity force, and if this plate is positive and this is a negative, the charge here must be a negative, so it can be pulled up, and the force here is QE. How do we know what? Well, it has to be, because if it was the other way around, it could not be balanced. It would just fall down. So QE equals mg. What was I looking for here? The Q, wasn't it? But I'll put the minus in because I know it should be a negative charge. And I have a formula for the E, it's V over D. Right, so the M times the G, what's the D? What's the distance? And the voltage? (9.81 times 10 to the minus 7). 981 nano coulombs. That's the answer. Yeah?
You don't care about the minus, right?
Oh, sorry, I lost my minus. I should have it in, yeah. No, we do care about the minus because it's a charge, and a charge can be a positive or a negative.
Yeah.
Yeah. A minus.
Not a minus.
Oh, must be, yeah. Must be minus, yeah.
Even if we didn't know that point, the charge is minus.
Yeah.
And you know, like minus 9, 8, so we could know the minus.
How
It
do
is
you know
minus
it's minus?
at the end.
Oh, you mean just write the minus in at the end?
Yeah.
Oh, yeah, totally fine.
No.
What?
If we didn't know the charge of that particle.
Was minus?
Yeah. We just made equation like that.
Yeah.
And
With no minus.
Yeah, with no minus.
Yeah. Will we get minus here?
Yeah.
No. The only reason I got the minus here is because I had to write it in.
Because it is minus.
Because it's known to be minus, yeah. Continue. Now, number 3 is an interesting one. Monica says she finds it very interesting. Right, Monica? So, you have a factory. So, you've probably seen this. You have your factory, and the factory often has a very large chimney stack. Now, what might be the reason for the tall chimney stack? Two reasons, yeah, that and that. First reason is you want to get the dirty smoke away from ground level and your workers. But the second reason is that you can use the long chimney to clean the smoke a little bit. Let me explain. What will happen is the smoke will rise up the chimney, but actually the dirty smoke has a negative charge. So if the factory puts 2 metal plates in the chimney and puts well, actually this could be the voltage around it, couldn't it? What did I say? We don't know the voltage. If it can put a large voltage here, it can make a electric field like this. Just like what we did in class. Why might you do that? Well, if this smoke has a negative charge, then what will happen is this plate will be positive, this plate will be negative, and if this is negative, it will move left or right. Left. So as the smoke is rising, it will move to the left and stick to the plate. Now, not all of the smoke will stick, just the dirty part of the smoke, the part that has the negative charge. This means when the smoke comes out of the top, you have taken some of the dirt, the sticky, negative charged dirt, you've taken some of it out. Okay? Now, my question then is, well, let me just write down some more information. You actually know exactly what the charge is. It's minus 10 to the 10 coulombs per particle, yeah. What else do I tell you? Coulomb, yeah. Huh? Oh, well, I'm just putting the minus in because I said it doesn't really matter. If you call this a plus, you'll still get the same answer. Oh, sorry, here. Sorry. I was talking about this. What else do we know? We know the mass as well is 10 to the minus 5 kilograms. And you also know that the smoke is moving up with a speed of half a meter per second, and the length of the chimney is 10 meters, isn't it? Yeah. So my question is, what's the voltage? Now think about this. If the voltage is too small, what will happen? As the dust moves up, if the voltage is too small, it won't be a strong enough acceleration and it will leave the chimney before it hits the plate. If the voltage is very, very large, then it means it will very quickly hit the plate. you want to find the voltage that just about works. Because if the voltage is too big, okay, it works, but then the company wasting money, but also it's more dangerous to have a high voltage. You know, high voltage is dangerous. So you want just enough. So what is the worst case? The worst case is that the dust starts on the right and you must get it all the way to the left before it exits. This is the worst case, and this is what you need to make the voltage do. You need to have enough voltage so that anything that starts on the right will make it to the left before it exits. Now think about this. If the smoke is going at 0.5 meter per second and you have 10 meters of pipe, how much time does that give you to catch it? How much time do you have to catch the dirt?
50.
No.
20 seconds.
You have 20 seconds. 20 seconds to catch the dirt in the chimney. Okay? So from there you can get it. I'll give you a hint. From the time you can work out the acceleration, and from the acceleration you can work out the force, and from the force you can work out the electric field strength, and from the electric field strength you can work out the voltage. And the force, remember, is acting to the left.
It will be more than 20 seconds.
Why would it be more than 20 seconds?
Yeah, it's not
What?
exactly vertical.
Who said it's not exactly vertical? Most chimneys point up. How many chimneys do you know?
From right to left. Sorry.
Ah, but I said in the question, did I say, I think I said it's rising at 0.5 meters per second. Yeah, rises. Rises means a change in height, not the speed. So it gains 0.5 meter of height, regardless of the direction. I understand you were putting the 0.5 on the hypotenuse of the triangle, yeah. The question? Yeah. Oh yeah, I didn't draw this in. The distance here to here is 0.3 meters. An answer? Yes. Yes. Yeah, that'll do nicely, yeah. What's the S though? What's the S? Yeah. Okay, I'll go back to the picture, KJ. No? Are you writing down everything word for word?
Yeah.
Ah, you can get that from the video. I want the picture up for people to see.
Yeah, teacher.
Now, I still want you to write it down later though. Yeah?
If there's no acceleration, does that mean that F equals to 0? Because F equals to anything.
No acceleration in which direction?
Upward.
Yeah, there's definitely no vertical acceleration, but that's not what I care about. We're looking at the particle moving horizontally from right to left. Definitely accelerating because it's being pulled to the left by the plate.
Okay.
But you're right, there's no vertical acceleration.
Oh, but that's horizontal.
Oh, definitely, yeah.
Oh, okay.
Yeah. Oh, the question. Okay, there you go.
Sure. 0.03 doesn't remove.
0.30 very much matters.
Yeah.
But yes.
Oh, yes.
Yeah. Changed your mind. Got an answer, Monica? Yeah. Yeah. Doesn't matter because you're looking at the worst case to catch one of the dust particles, so you'll be able to catch them all. Just like Pokemon.
The distance straight.
Boom, have an answer? What you got?
45.
1455 is pretty bang big. What did you get?
45.
Yeah, okay. Yeah. Thinking maybe somewhere in between. But yeah. Let's have a look. Back to the question. Okay, so look. Here's the deal. We know the time. We have 20 seconds to catch it. And we're looking at it going from right to left. So the U is 0. The V we don't know. The A we would love to know. The T we have 20 seconds. And the S is 0.3. So using S equals UT plus a half A T squared. So 0.3 equals 200A. So A is 0.3 over 200. I will just leave that for the moment. Well, no, actually that's easy enough because that's 0. If I divide that, is that 0.0015?
Yep.
Like this?
Yep.
Meters per second squared. Now that's a small acceleration, so it very slowly is accelerating the positive plate. But you also know that F equals ma, so A equals F over m. And you also know that F equals QE, so A equals QE over m. Yeah. But you also know that E is V over D. So you can say that MdA over Q is equal to V. Do we know the A?
Yeah.
Yes. Do we know the D?
Yeah.
Yep. The M?
Yeah.
And the Q?
Yeah.
So let's see what we get. Is 45? Okay. 45 volts. So the company needs to use at least 45 volts and then it can capture the dirt. No, it'll catch each one. We're just looking at one as an example. This is what actually happens at these factories. So at the end of the day, all the dirt is on the pipes, the chimney stack. And then at the end of the day, there's this machine, it's like a hammer, and it hits the metal plate inside the chimney. And all the dust from the day, it falls off and down and is collected. So, there's like a giant ashtray at the bottom. The hammer strikes the metal shakes and it falls down and you get it. And this is good because it means that dirt that you caught was dirt that didn't get out and didn't land on buildings or people or clothes. You know, so it is like you took that out from the environment, and perhaps that dirt could be used or recycled in some way, used in some kind of fertilizer or chemical process like this. So this is the type of stuff that you might study if you were doing sort of green engineering, environmental engineering. Is anybody thinking of that? Is somebody? Yeah. So, you know, this is the type of thing that you might have a look at. These are techniques to sort of clean the output from factories. This isn't really what the future would be, because what would be the thing people want to take out from the output of factories? What?
Money.
No, if money was floating out of this, yeah, you'd want to take that out, but I don't think euro coins are floating up the chimney stack. So what would you nowadays want to take out of the smoke? Yeah, but what? What one? CO2. Okay, so nowadays it's not the dirt you want to take out, but you would want to try and take out the CO2. Well, this is the question. How? Yes. Like, the problem is, it is not easy to take out the CO2 from it. It's not, because the CO2 doesn't have a charge. Well, it's charge neutral, so you can't pull it out by using a field. So you would need to use some kind of chemical reaction, like with the lime, perhaps, to cancel it. You know. Ionize it? Possibly, I don't know. You see, this is the problem. In the future, if people were to reduce the CO2, it's not enough to have electric cars and stuff like this. Engineers need to figure a way to take the CO2 out of the atmosphere that's already in the atmosphere. You know. Again, this is what the area of research is. There is ways to do it, but it's expensive. Yeah. The only problem is you would need acres and acres of forest to actually do it. Yeah, you wouldn't be able to put enough plants in there to do it.
Can we connect the pipe into the forest?
Yeah, okay, engineering students, you'll need to think of better solutions than this. This is like cartoon solutions. What about if we capture all the smoke and send it in a rocket to the moon? Okay, just before we finish, there's one more example I want to do, which isn't here, but it's an important one. This is an type of experiment, but it's not too difficult. So this is called the oil drop experiment. Okay. Yeah. Negative, positive, negative, and you have a voltage here, and you have a distance here, and you drop some oil drops in here in the field. And some of the oil drops move up, and some of them move down, and some of them move up, maybe some of them move down. How could it be that some of the oil moves up and down at the same time?
What?
How can some move up and some move down? Well, it's because the force must be zero. If the force is zero, then they move at a constant speed. So some of them could be moving up, some of them could be moving down. But if they all started at the top and were dropped, then they should all be moving down because they were released from the top. Anyways, what you do is you change the V so that they all move at a constant speed. If they're all moving at a constant speed, then what does the F equal? 0. So that means the QE equals mg. Yeah. Okay. Now, the E we know it's V over D equals mg. So the Q equals mgd over V. Okay, we know the G, we know the D, we know the V, and we could measure the M. For example, imagine that this all came from, let's say, 1 gram of oil. Yes? And you counted 1, 2, 3, 4, 5, 6, 7, 8 little oil drops. Then you know that the mass would be 1 gram divided by 8. Okay, so you can know the M. So you can know all of this. So can you know the Q? Yeah, you can know the Q. So in this experiment, what you do is you start writing down and calculating all the different charges. So you get one charge, you write it down. You get another charge, you write it down. You get another charge, and you write it down. And you look maybe at all of these numbers. And after a long time, when you think about it, you notice that all of these numbers can be written as, for example, this one could be 5 times some number. I'll call it x. No, not this. 4 times some number. Maybe this one was 10 times some number. This is 2 times some number. Maybe the last one was 1 times some number. Like, I'll give you an example. 6.5 7 0.5. There is one number that I can put into all of these. 0.5 is the biggest number I can put into all of these, because this one I can say is 13 times 0.5. This one here is 14 times 0.5, and this one here is 1 times 0.5. So if you do the same thing here, and if you can find this number, if you think about it, what you found is actually E. Because the charge can only ever be a multiple of E. Because the reason it has a charge is because it has an excess or a deficit of electrons. So if you get enough of these numbers and you look at them long enough, you can figure out which number must divide into all of them. And whatever that number is, that's the E. So by doing this experiment, you can calculate the charge of an electron. And this is how, what's his name, what's his name, not Minkowski, I don't think. Oh, I can't remember his name right now. It begins with an M. No, I don't think it's Minkowski. Not Oh, what is his name? No, it's not. Anyways, I can't think of his name. Apologies, he's not listening. He's dead. I can't think of his name. Anyway, whoever it was, this is how he did this experiment and how he was able to work out the charge of an electron. Which, if you think about it, is impressive, because the charge of an electron is very small. But by doing this experiment, you can work out the charge of an electron. Yes, I see. Oh, okay. Is it water?
Yeah, water.
Okay.
The name is Robert.
No, it's not Robert.
Yeah, it's Robert A. Milken.
Yeah, it was the surname I was thinking of. Milken, is it?
Yeah.
Milken. This experiment will be important later.
Are we going to do it?
No, not this one, but what I'm saying is this experiment lets you calculate the E easily, true? You can do another experiment later that lets you calculate the mass to charge ratio of the electron. Yeah, and you realize, wait a second, if I know the charge and I know the mass to charge ratio, then you can know the mass. You already know the charge of the electron, and if you know the mass to charge ratio and the charge then you can know the mass of an electron. And this is how you can find the mass of the electron, which is impressive because it's so small. It's very interesting, I think, very interesting. Robert.
Yeah.
Robert's experiment. Okay. Right, so we've done this one here. I'm taking my time with the field section of the course because I believe you all probably find it a little difficult. But when we go on to the atom and the waves, we'll move back at normal speed. But for now, I'll move at half speed for the fields because of its difficulty. Yep. Yeah, but you still have to do the ones that are in section A, but I would recommend avoiding it in section B.